Okay, so this was the rate of change at any number of days after the oil rig started to leak. And the first thing we did was we sketched what would the volume function look like. And we said the volume function would always be increasing. Why?
The rate of change is positive.
Agree with that? So the rate always stays positive. The volume expelled is always going to be increasing. And then what does the low point on that rate of change signify? The minimum rate of change going to what effect or what's that? Does that mean minimum volume expelled? In terms of the volume accumulating, how is the volume accumulating right around 1.8 days?
Almost constant.
So it's accumulating the slowest, right? So it's accumulating the slowest of any time in this period of days. And you see that in the rate graph, or how do you see that in the accumulation graph? Yeah. Right, so it's going up most gradually, right? So it's like the most shallow part of the curve. It's going up the most gradually because it's the lowest rate. Okay? And so then what do we say? So our endeavor is that given this rate of change function, we want it to define that B function precisely, like get a definition, a real definition for that function, given the rate function, okay? Not just a sketch. So this is, like the goal is the definition of that function that I'm showing in blue there. Okay, so we said that any point on the rate graph gives us the rate of change at that time. So this is the point 0.97, 9.68 meter cubed per day. What does 9.68 meter cubed per day mean?
So with that, like, for any small change in the days, the corresponding change would be 9.68 times the volume. Oh, the change in the days.
Right, so exactly. So given any small change in days, the amount of oil expelled, the additional amount of oil expelled would be 9.68 times that number of days, right? And it has to be small. Why does it have to be a small change now? Yeah, the rate is continually changing. So we need a moment, right? We need a moment, a small enough interval where we can say that the rate is essentially constant. And so for the rate graph, so that's not showing, that's still showing a changing rate. You see that? Because that's a rate of change graph. It's not an accumulation graph. If this were accumulation, that would be showing constant rate. But this is still showing changing rate. So how do we think about a constant rate in this moment at 0.7 days? How do we think about that? Horizontal, right? Horizontal. So this is a rate graph. So for a rate to be constant, we need a little horizontal piece. And so we assume in this moment, in this very small amount of days, we're going to assume that the rate is essentially constant. Okay? And so then what did we do? We were looking at 0.7013, right? So, upside down, that would be very difficult. Okay. First of all, I had to correct this, right? This is supposed to be 0.7013, right? And so what do we do? We said we're going to, we know that at 0.7, suppose that it's, the amount of accumulated oil is 13 meters cubed, 13.15 meters cubed. And then we want to find the volume at 0.7013 days. What are dx and dv in this case? So what is dx? Serenity. Okay, so the change in x is 0.0013, which I think is about right there. And then, so that dx, that's a horizontal because our x is our horizontal coordinate. All right, what about dv? dv. How would we find dv now that we've chosen a dx? This dx is 0.0013. How? What about dv? How? We're trying to find the final v, so we can't do final minus initial because our goal is the final v.
V 0.7013 minus 13.50.
No, it's not a minus here. Given the change in x, right? Given the change in x. This is all about constant rate of change, right? What's our constant rate of change, right? Given the change of x, the change in v is always Melanie.
Oh no, I just had a question. Are we saying the initial is the 0.702 or 0.703?
No, we're not doing this. There's nothing to do with this. We're doing the first example.
Okay.
Yeah, so suppose we're starting here at 0.7, right? This is 0.7, 13.15. That's our initial. Okay, so did you figure out what dv was, Hal? Based on constant rate of change?
Yes. 13.50 plus.
No. Kira, what is it?
If we think of dv as like dy,
Mm-hmm.
it would be equal to mdx.
mdx, right? mdx, so what is it? And what's m? It's 9.68. We have see, in this moment, we're assuming a constant rate of change at 9.68. So m is 9.68, and dx is 0.0013. Constant rate of change. Given a small change in x, your change in y, or in this case v, is the rate times your change in x. Constant rate of change. So that took us up somewhere. I don't remember where. Okay, whatever that equaled. Anyone have it? 0.01. I'm not going to be able to do the 84. 125. Okay, so that's up to, so here's 0.1 and a quarter. I got lucky, right to the right spot. A little bit too far, right about there. Okay, and then, so now what is V of 0.7013? Do you know? Just express it, right? I'm not asking you to calculate any numbers in your head.
It
But
would be 3.15 plus the mdx plus the 9.68 times 0.0013.
right, so it's going to be the initial y, or initial volume, plus the change, which is this down here. Okay, and then what we didn't do last time was What about in this moment, what about every correspondence point of a number of days and a time? I'm sorry, a number of days and a volume, right? Okay, so how would we go about representing every correspondence point in this moment for this constant rate of change? What would we do? Charlie?
So we start off with like picking an arbitrary
Right.
point, like an x, y,
So we can say xv.
or oh yeah, x, v.
Although we're calling v the name of the function, so maybe y is better. Okay. And then what? Anybody? Yeah?
I think basically some of the variables just how we did before, so then it'd be dx equals 0.7 minus x, or no, x minus 0.7.
So now our dx is
X
good. X minus 0.7, right? Done this before. Then? Sure.
Okay, then we set up dv, so then dv equals mdx.
9.68 times.
Dx, x minus 0.7.
Good. Finally, any volume in this moment then is y. Say y. Is say v of x, right? Equals 13.15. Yeah.
Plus 9.68 times x minus 0.7.
So now we've got, look, we started out with how much do we have, how fast is it changing every moment? So we picked a moment, 9.68, or so we picked a moment around 0.7 days, and we have how fast it's changing at that moment, 9.68. And what did we just find? What is y or vx? It's how much we have at every moment, right? That function vx is how much we have at every, sorry, not every moment, at every time in this moment, right? At every time in this moment. Pick a time, any time in the moment around 0.7, that tells you how much volume of oil is expelled. Okay, so now all we have to do that, just do that, what we just did for every moment. What do you think? So we're going to go back and do 0.695. Let's see, where's this? Yeah, this is 0.966. So we'll go back and do, say, go back to like 0.95. 0.695. And then we'll do 0.69, and then we'll do 0.685, and then we'll do for every moment. What do you think of that? Sound like a plan? Okay, obviously, right? So we would be here all semester and all year, right? Trying to do that. But this is, right? This is the heartbeat of what's going on when we say we know our rate of change and we want to know how much we have, right? And we could imagine doing this for every moment, and then we'd have the entire volume function, right? We'd have the entire volume function, not just this one moment at 0.7. So we'd have 1,000 little equations like this. Okay, but obviously we need something a little more streamlined, something better to get us to generate this volume function for all moments, rather than trying to do it one moment at a time. Right? Not a good. So it's great for the concept, but it's not great as a strategy to actually finish the job. Okay, it takes too long, way too much to do. Any questions on this? Questions on this slide? All right. Again, this is our journey. You know how fast something is changing at every moment? You want to know how much you have at every moment? The key is constant rate of change. So just watch this, right? So The whole key here is dV equals mdt, right? Getting that little change in volume from a little change in time. And then final volume is the initial plus the change, right? These were the foundational tools that we used when we just did that, finding that volume function. So look, given a constant rate, what? You know how fast something is changing every moment? You can find out how much you have, right? So given m, you find a little bit of E, a little bit of accumulation, and then you can find a net or total accumulation. So this is embodied, this is kind of a summary of that process. You know how fast something is changing every moment, you want to know how much you have at every moment. You start with m gets you dVs, and dVs allows you to build a volume function. But we need a different strategy to make more progress at developing the whole function, not just taking 10 minutes to do one little moment, right? So we need a different strategy here. So here's what we're going to do. What we're going to do is we're going to break up these 2.5 days into equal intervals of days. And then we're going to look at various rates in those intervals. So how could you represent that point right there? So this point right here. How could I represent exactly the coordinates of that point? What's that? 0 and R sub v, right? R sub v, exact rate of change of 0, right? And then we could estimate that to be, what's an estimate for that rate? About 20, I heard 28, that's fine. Okay? About 28. So this is what? This is at 0.4, so it would be 0.4 and R sub v of 0.4, and that's about 17.
Should we start writing these on the graphs we have or save?
Just hold on a second. Yeah, so you don't probably want to put these ordered pairs. Maybe be doing something else. All right, and then similarly, we could do this for all the points, and this is what? Every 0.4 up to 2, or up to 1.6. Okay, and then here's our strategy. So rather than going a moment at a time and assuming a constant rate for a moment at a time, we're going to assume a constant rate over these intervals. How many intervals do we have? 1, 2, 3, 4, 5 intervals from 0 to 2. We're going to assume a constant. So these are not moments, right? These are not moments. They're way too big to be moments. Or you can just say they're very, very big moments, right? Very large moments. And we're going to assume a constant rate over these very large moments. So in the first moment of 0.4 days, we're going to assume it's constant, and we're going to use the rate at the left side of the interval. So what will the rate of change be for this whole interval from 0 to 0.4 if we use the rate at the left side, or this is the beginning point of the interval? What will the rate be in that interval, or in that moment? Did you understand the question? So in each of these, so do you see that we have moments of 0.4? So I'm demarcating moments of 0.4. And in each one of those moments, these large moments of 0.4 days, I want to have a constant rate. I'm going to get that constant rate by taking the actual rate at the left side of that moment, or the starting value. So what will the rate of change be in the first moment? What will the rate be be in the first moment from 0 to 0.4 if I'm going to take the rate of change at the left side of that moment. The actual. Well, that would be the average. That now you're trying to average them. We're going to take the rate at the left side of the moment and make that be the rate for the whole moment.
So,
It's so easy it's hard, right?
is it
Does it have anything to do with 17? We're going to take the rate at the left side of the moment and let that be the constant rate for the whole moment.
You can't divide
So we're going to take the rate of change, the actual rate of change at the left side of the moment. What is that?
Just 20
Well, that's an estimate, right? What is it exactly?
R
RV of 0, right? Isn't that the rate of change at the left side of the moment? Yep. Is there anything?
Oh,
See that?
because, oh,
Here's the moment from 0 to 0.4. And what x value is the left side of that?
constant, okay.
What's the left side of that moment? 0, right? X equals 0. What's the rate of change at 0? RV of 0. Right? So watch. So then we're going to take that rate. So what will it look like? We're going to kind of form a new rate graph. What will it look like if we make that rate of change, RV sub 0, be the constant rate for that whole? This is what you're doing on your paper now.
So we can write this down.
No, don't clutter up the graph with these points. But what I want you to write, I want you to show is a constant rate of change through the first moment equal to the rate of change at the beginning of the moment, the actual rate of change at the beginning of the moment, the left side. So what would that look like? What's that? The rate of change is not 0. 0 is the x value. What's the rate of change at 0? RV of 0, right? And so what will it look like if RV of 0 is the constant rate for that whole moment? Right, watch, you ready? Watch, this is what it looks like. What did I do? We took the rate of change at the left side of the moment and we made it constant for the whole moment. All right, so tell me what are the coordinates of this point right here? So just as a practice, sort of just to see if you got it. If you had to write the exact coordinates of that point, what would it be? Nope. See if you can do it. Write the exact coordinates of that point on our new, because we're building a new rate graph, right? We're building a new rate graph. What are the coordinates of that point in the new rate graph? Is that related to what we're doing? Just as long as it is, that's okay. But if it's not related, okay. What do we think? So x and y coordinates at that point.
Would the x just be 3?
Not 3.
Oh, 0.3.
Okay, 0.3, right? 0.3 and RV of 0. RV of 0, good. Because the rate is always RV of 0 in this moment. See it? Make sense? Okay, now we're going to keep doing that, right? So for every moment, I want to keep constructing this new rate graph so that in every moment there's a constant rate, and that constant rate is equal to the rate at the left side of that moment. So what would that graph look like?
Yeah, everyone.
Go do it. So do it on your graph. Okay, see if yours turned out like this. Ready? Is that what you got? Okay, this function we're going to call R. So R sub v is what we use for exact rate of change. This R sub v there. So that's exact. Our changing rate function, right? And then R is going to be our approximate or pretend rate of change. Right? It's trying to be like the exact rate. It's trying to be like the exact rate. Is it a good approximation of the exact rate? Is it good or bad? Pretty awful, right? Pretty awful. Okay? Yeah, so especially at the beginning, right? So these last two intervals, not too bad, right? The last two where the rate is kind of more constant, but at the beginning it's not doing a great job at all. So why did we take this beautiful exact rate function and just butcher it, right? We just created this new one that's trying to be like it, but doing a horrible job of trying to be like it. Why might we have done that? So how did we do? So what did we do? How did we make the pretend rate function? With what? Horizontal lines represent what? Constant rate of change. So why might we have? So even though we made this new rate graph is a very poor representation of the exact, but it's based on constant rate of change. Why might we have done that? So we don't have it yet, right?
Yeah.
So we're not analyzing it. What are we trying to do? We're trying to make it. We're trying to build it, right? Does it help us build it? We can't build it without it, right? So we can't build a thing without it, without constant rate of change. Remember this whole thing that we just did, right? The whole thing we just did. dv equals mdx. How do we work towards accumulation? First we get little changes, right? And then we do v final equals the initial plus the change. So here's the kind of the heartbeat of finding amounts, right? Or little bits of accumulation. Or modeling the accumulation. What does this all depend on? What does all this depend on? Why can we do this? Constant rate of change, right? Constant rate of change. You can only do all this with constant rate of change. So we're kind of making this pretend rate function based on constant rate of change, so we can apply all this math we've been working on for 3 weeks, right? Over and over and over and over and over again. All that stuff, this equation of a line, right? Building the equation of a line from a rate of change that we've been doing for 3 weeks is based on constant rate of change. So although this is not a good approximate of the exact rate function, it has this very, very helpful quality, constant rate of change, that allows us to make headway toward our goal, which is to build the accumulation function. Okay, so let's do it. So now can you write, piecewise function. Can you write a piecewise function that represents that blue function R? Can you write the function? So you can do this below your graph. Can you write, and I don't want approximations, I want exact representations in your pieces, of values in your pieces. Can you do it?
So we're not doing like the estimate 28, we're doing
Nope, I don't want you to use any estimates in this rate function. I want the rate function to be based on exact values. I want the rate function to be based on exact values. Okay, Kiara, can you get me started on this? RV of 0. 0 to 4? 4. That's okay. You got her going. All right, how'd she do? It's good? Okay. How can you do? What's next?
RV 0.4 if 0.4 is smaller than x and smaller than 0.8, which means the interval is 0.4 to 0.8.
Okay, now this seems a little backwards or counterintuitive, but I'm going to start making these open on the left and closed on the right. And you may think that doesn't make any sense, right? You come to the new interval. We want to grab that rate, have it be equal to there, and then take it to the end and have it be open here and then be closed on the left, right? We're going to see. You just have to trust me that we have to do it this way. All right. Anyone know why we're going to have to do it that way? Okay, so you remember. Okay. All right. Tino, what's the next line?
It would be RV 0.8 from 0.8 less than x less than or equal to 1.2.
Okay, and then we just keep going like that. And one more. Okay. So this is our pretend rate function, or our approximate rate function. It's trying to be like R sub v, but not great. It's not great, but it has this key quality. What's the key quality that we need? Constant rates of change. With constant rate of change, we've got the math. We've got it under our belt so that we can use it to build accumulation, amount of oil, right? Amount of oil, or accumulation of oil. All right, so now we're going to build, based on that rate function, we're going to build an accumulation function now. And so you see this is making a lot more progress because we just wrote down a rate function for the whole 2 days. And now we're going to write down an accumulation function for the whole 2 days, not just one moment. But the caveat, the downside is that this isn't going to be very close, right? Because this rate function is pretty terrible, right? But we're using the principles we know we need to use, and we're getting a final product. At least we're getting something, right, to start. Okay, so accumulation. So how are we going to write? And so we're going to have the same intervals, right? So if we have a constant rate of change, what will our accumulation function be like at a constant rate of change? What will this say in the first interval? So if you have constant rate of change, what does the accumulation, what's it like? What's it going to be? We've worked hard on this. No, 9.68 here. That was at point. That was at 0.7 days only. So this is now we're looking at the whole bigger picture from 0 to 2 days. But so in the first interval from 0 to 0.4, what's this going to be like? We've done it many times in the last 2 weeks. Many, many, many times. What are you saying, Serena? Is this going to be dv? So we're trying to graph.
Oh, it would be 0.
So you just have to click into all this, all what we've been learning, right? So we've done this over and over and over again the last couple of weeks. But you just have to kind of apply it, right? You have to see how it, you have to have that accessible, right? You have to have, and see that it applies, right? So we've got a constant rate, and what are we saying? We want to say that
What would be the rate times the changing?
okay, that's part of it. So the rate is okay. So we could use RV0, but we've built so that in this interval, what is RV? So in this interval, when we go from 0 to 0.4, if x is between 0 and 0.4, we're going to get what? If we use r, we're going to get RV0. So let's use the function that we made, right? So r of x times what? What's that? That's 0.4? What's dx in this interval, right? Every point in this interval, right? Every point. Maybe it's because we don't have the picture this time. So it's because we're not drawing the picture. Is that what's... No, a function is describing every correspondence point, not just the last one. If you just want 0.4, you're just trying to calculate the last correspondence point. I want every correspondence point in this interval. Remember what we did with every correspondence point? Okay, so tell me, Rx times dx. What's dx for every correspondence point in this interval? X minus 0.4. Remember? It's just that you don't have the picture in front of you, right? It's the same thing. You just don't have the picture in front of you this time because it doesn't exist yet, right? We need anything else? So what's the initial? 0, right? So volume initial plus the rate times the change in x for any x in the interval. Is it familiar? So what is the rate? 28. So it's gonna, so at 0.5 would be at 14. Right, so what are we doing? We're writing every single correspondence point in this interval. Right, so it's kind of like we did the what? X comma v, x comma y. We started with what? Dx. Dx is x x minus 0, right? X minus 0. It's just x. In this first interval, it's just x minus 0. So this dx is x minus 0. dv is what's dv? m dx. So it's r of x times x minus 0. And then finally, y. Again, the y for every point in here. Initial 0 plus r dx, right? So then we get that's the first interval, right? Okay, so now we're going to go on to next interval. Can you do it? So I want you to write from 0.4, 0.4, less than x, so equal to 0.8. All exact values, right? All exact values. So that's going to be something like oh, I went too far. Anybody think they got it? 0.4? Here? Okay, 0.4 plus? How, you agree with that? Do you know you agree with that?
Sure.
Meaning you think there's a mistake, or you don't know at all?
I think there might be a mistake because the point 4 plus r of x minus 0.4 would not line up with the previous line.
Why not?
I think the 0.4 needs to be a of 0.4. Because if it's just 0.4,
What is 0.4? What is that number?
that's like the left x, like an x initial.
X initial, right?
Yeah.
X initial. And what is this? This is final volume, right? Final volume is going to be X initial plus the change in volume. Do you want to change it? Right? Because V final is what? V initial plus dV. What is this? Is this V initial? It's X initial, right? This is X initial. This is days. You see? So what do we need? We truly need V initial. So how do we represent V initial? So if X initial is 0.4, then what's V initial, right? What's V initial?
Oh.
This is why we're putting the equal signs on the right side. Because we can get it from here, right? Just like we did in here. So here, what should it be? We don't have a function named V. What's our function?
If we wanted to go off of that for the first one,
Mm-hmm.
would we have to say A of 0?
No. We just know the initial amount is 0. But you can't, then you'd be stuck in an infinite loop in this line. A of 0 hasn't been defined yet, right? A of 0 comes from this line, so you can't use it in this line. So we had to use the actual number, the value. But now when we get to the end of this interval at 0.4, this will be able to generate the final volume from that interval. which we can use in the next line. But you can't do a of 0 because then you're in an infinite loop in here. It's trying to figure out what a of 0 is by plugging 0 into this line. You can't do it. So we can just say, we know that there's no volume at day 0, so we just put 0. Does this make sense? So then the rest should be easy, right? So once we get those first two, it should be easy. So now we're going from 0.8 to 1.2, 1.2 to 1.6. So it should make sense and it should feel familiar, right? It should make sense. It should feel like familiar, like this is what we've been doing over and over again. Just now we're just kind of now we're really using it. Now this is why we learned it. Now we're really using it to build a accumulation function. Okay, so Melanie, what's the next line?
A 0.8
Uh-huh.
plus R of X times X minus 0.8.
And Charlie, what's the next one?
A of 1.2
Uh-huh.
plus R of X times X minus 1.2.
And then so okay, so let's track. So if you put a of 1.5, if you put 1.5 into this function, I want you to, with a partner, track what it does. So I'm going to put x equals 1.5 days into this function. And I want you to track, how does it figure out what the accumulated volume is? Is it approximate or exact? Approximate or exact accumulated volume? Approximate. It's based on the blue rate graph, right? So how does this function calculate the approximate accumulation of oil at 1.5 days? What does it do? So work it all the way through. Go, talk it through. It's going to accumulate in every interval, right? Just linearly, right? So how does this function work? What does it do? Did you guys figure it out? Charlie, what happens?
So when, so x equals 1.5.
Uh-huh.
So go to the interval that has 1.5, and that's x from 1.2 to 1.6.
Right?
So then, I guess two things happen. So you get the rate of change, so r of 1.5, which takes us to the rate of change for that interval, which is r of sub v of 1.2.
Right, so we're going to RV of 1.2 right here. Did you see that? Okay, cool.
Okay, so that's our rate, and then we also find the change in x.
Uh-huh.
So it plugs in x there, so that's our dx. And then
Which is what?
0.3.
0.3. So it's going to be 0.3 times R sub v of 1.2, which you get from the rate function.
And then it adds it to the initial value, which we get from the previous line, a of 1.2.
Well, so when the function sees a of 1.2, then what does it do?
And it goes to the line above, where,
Yeah, it's going to invoke the function.
oh yeah, it's like, okay,
It's going to invoke the function and do what?
find like the interval where that x is.
Right. So now the function's going to have to operate a of 1.2. So it puts the 1.2 in here, and it goes to this line. And what does it do? 1.2 in for x, 1.2 in for x. It gets the rate, which will be, what will the rate be now? This rate? R sub v of 0.8 times 0.4, and then it's going to add a of 0.8. How's it going to do a of 0.8? It's going to plug in 0.8, and it's going to invoke the function again. Right? And it's going to keep doing that through every line, right? To keep getting these previous a's, it has to keep invoking itself. But then in the end, it's gonna have what? All the accumulation. It's gonna be that. So really, what's it gonna do? In the end, it's gonna have a of 0.4 plus what? A of 0.8. Oh no, that's not right. Because a of 0.8 includes 0.4, so that's not the way to write it. You can't write it that way, right? Yeah, so in the end, it's going to do a of 1.2, but to get that, it's going to use a of 0.8, and to get a of 0.8, it's going to use a of 0.4, etc. Okay, so this is better because now what? We have a volume accumulation function for all 2 days, right? And it didn't take us all semester, right? Doing it one moment at a time. But what's the downside to this? What's that? Oh no, well, so like we can let technology do that. That's not too bad of a. That's not too bad. It was the real issue though. That's bad about this. Yeah, it's a bad approximation because our rate function is bad, right? So that accumulation function is based on this, the blue step function, which is badly reproducing our rate function. Okay, any questions on this? But we're making progress here. We're making progress, and you see that we're actually putting to use this stuff, all this constant rate of change and building the function of a line, piecewise functions. All this stuff is coming together in order to kind of achieve this result that we want, right? Given you know how fast something is changing every moment, you want to know how much you have at any moment. So we have a version of how much we have at every moment. It's a crude version. It's not a good approximation, but it's something, right? In terms of you know how much of it you have. And does this kind of look like the v function we sketched? Kind of looks like it, right? It's just a piecewise linear though. These are all linear pieces, but it looks pretty much like what we came before. So at the beginning of these, is the actual accumulation less or more than this? Is the actual accumulation going to be lower or higher than this? Is this too high or too low? You should be thinking it's too high because these rates are all too high, right? At the beginning. Pretty good at the end, a little bit too low at the end, but for the most part, this is too high, right? It's approximating with too much accumulated oil. Okay, so let me show you the next two projects that you'll be working on. And I'll just so normally in last year, today was the due date for the next GC project. So we're like 1 day behind. You kind of had half a weekend break there. Hope you enjoyed your break, your 2-day break. Normally there's always something to do in this class, so hope you enjoyed that. But let me show you the next two projects, which both relate to this. They both relate to this volume. Any questions on this before I erase everything? Does it make sense? Okay, so let me show you. Quit on me. Hope it comes back. This is the first one. Okay, so here's the first one. You see we got the rate. I got showing you the rate graph over there. And there's two sliders. There's the N slider, and then there's this A slider. Okay, A chooses different current value of X. See that? So just look at the left graph. So right now, A is 0.06, and so we're starting, our left side of our moment is 0.6. And if I change A, I can change A. Here's 1.8. Now the left side of the moment is 1.8. Okay? And then N varies the value of X in that moment. See that? So when N is 0, you're at the starting value of the moment, in this case 1.8. And when N is 1, I guess 0.5. When N is 0.5, then you're at the end of the moment. So these moments are 0.5. So we just did moments of 0.4, but this is a kind of a roving moment of dx of 0.5. Or sorry, delta x. Okay? Now, so that's what happens there. So what in this animation then, you pick your starting value of the moment. So I can pick, say, 0.9. And then as you change N, what happens over here? It shows you a little triangle which relates to what we've been talking about. So now look at the right screen, the right graph. So what is it showing? It's showing, starting here, it's showing the accumulation of oil for that moment at the constant rate, whatever the constant rate of R sub V of 0.9 is. So then if I change the starting value of the moment, and then I change N, okay, so, oops. So then this is the same starting value of the moment, but notice what happens here. Do you notice that if I come back here and where the rate of change is higher, so now here's the high rate of change, look what happens on the right. It's depicting that rate of change. You see that? It's depicting the accumulation at the rate, whatever the rate is, according to the left side of the moment. So here's the highest, right? It's the highest rate. And over here, it's the lowest. So here's the lowest rate of change. See that? Now, when you build your file, you're not going to put all those question marks in there. You're going to put notation that tells me that you know what those things are. Does that make sense? So you got 4 question marks and the ordered pairs. So what is that value? What is that value? What is that value, and then these 2 ordered pairs. So you're going to put in, you can use the symbol, right? That symbol notation that I showed you. So you have everything you need. It's just a matter of applying it, right? So, and then all the mathematics behind this is all the stuff that we've been doing. It's everything we've been doing. Any questions on what's going on here? Do you see what it does? Do you see what it, if I change N and change A, the effect is. Now, the one thing about this that's not accurate is notice that this like starting value of volume, notice it just is always here, right? It's just always along this horizontal line. So that's one aspect of this that's not accurate. So I'm just leaving that out, right? So it's just assuming that at any value, any starting value of the moment, it's assuming that you're always starting from this past accumulation, this amount, right? Instead of the true accumulated amount based on everything that's happened before. It's just always assuming, let me see, I think I put it at like 2 or 3. I put it at 3, I think. So the starting value of volume over here is always 3, regardless of what's happened before. Just to make the project a little easier, okay? So you don't have to worry about that. So you just always start, no matter where the moment starts, your starting Y value on this graph is 3. but then the rate has to match the rate at which this purple line is generated is consistent with the rate that you have for the moment that you chose according to A. Right? So when it's low, you get a low rate, and when it's high, you get the corresponding high rate. Does that make sense? So this won't be due Thursday. So, but I will probably. I'm going to show you in a second here. I'll show you the other one, and I'll let you work on both of them at the same time. Okay. So, but you need to show me some progress on this first one Thursday. So I'll walk around Thursday and just look that you have something going on by Thursday. Question 2.
When do you think this will be exactly today?
This one for sure Tuesday.
Okay.
So like a week from today. Let's say a week from today.
Okay.
And then depending on how much progress you have Thursday, maybe they both will be due Tuesday. So maybe they both will be due in a week. Let me show you the other one if I can find it here. Okay, now the other one is also related to what we did today, very closely. So the approximate rate function RV is graphed in its entirety by only one command line. Okay, this is part of that line. So this is this idea of what? The repeated parameters. So applying a line using a repeated parameter. So A is a member of 1 through 10. Okay, so that's the blue. So you can graph that blue using this technique. And you're going to use exactly that. You're going to use A as a member of 1, 2 through 10. You're going to use exactly that, what I typed right there, as part of your line, and it's going to graph the whole entire approximate rate function. Now, if you change n is the number of intervals being shown from 1 to 3. So here, n is 5. So we have 5 intervals from 1 to 3. If I come back here and choose n to be 1, it automatically, when n is 1, it shows you what that approximate rate function would be if there was one interval from 1 to 3. And if n was 7, that command line graphs that function with 7 intervals from 1 to 3. And then notice every time I changed n, it gave me the corresponding approximate accumulation function on the right. Just like the one we built today for n of 0.4. So here's n of 3. So from 0 to 3, there's 3 intervals. And then you've got the corresponding approximate rate function from 0 to 3. Control L. Like this, the RV.
Yeah.
Yeah, if you ever want to name a function with it, just do Control L and type it in, and then you got to get it back up to the center line to keep typing after that. Then you want to use your Control 9 for function notation. So I think, so here's the rate function. So you're going to use you can either write that down or just watch the video. I'm going to post the video. That is this rate function. It looks like this. So you're graphing the rate function in red, and then the blue step function, you get one command line. One command line to graph the blue step function, and it has to change as you change n. And then after that, then you're going to also include command lines to graph the corresponding accumulation function. Okay, so both of those, I'll post this video, and both those descriptions will be at the end of the video. And you need to have as much progress as possible by Thursday on the first one.